So this previous year question is a type of equimolar counter diffusion. So carbon dioxide and air which experience the equimolar counter diffusion in a circular tube. Okay. Uh, the diameter and length of the tube is given as 1 meter and 50 mm. And the total pressure of the system is 1 atmosphere pressure and temperature of 25 degrees Celsius. And the ends of the tubes are connected to a large chamber where the concentration are kept constant, and the partial pressure of Ca2 at one end will be 190 mm of mercury, and the other end will be 95 mm of mercury. And the diffusion coefficient is given. A combination is given as 0.16 into 10 raised to minus 4 meter square per second. Then we have to determine the mass transfer of carbon dioxide and air. Okay, that's what you have to determine. So first of all, writing all the given condition, given data. So we have diameter, length. Okay, we have diameter, length, and total pressure is also given. Temperature along the length of the tube is also given. These are all the given condition. The very first step in this type of question or equimolar type question, we have to determine the partial pressure at both the ends. Okay, this equimolar counter diffusion happens between two end, right? On one concentration region to other concentration region, and there would be a separate partial pressure for the component on both ends. So you have to determine first that partial pressure. Here I am in this question I have mentioned only carbon dioxide. So you have to find the partial pressure of carbon dioxide only. So partial pressure of carbon dioxide one end is given as 190 mm of mercury. Okay, we cannot use this equation. It has to be converted into bar first, then into Newton per meter square. Okay, we are for using every equation in the standard form. That means I need to convert in Newton per meter square or Pascal. Okay, 1 Newton per meter square and Pascal are same. So first of all, we have to convert the mm of mercury into bar. So one bar is 760 mm of mercury. So basically, this value can be divided by 760 not to convert into bar, and that bar can be one bar is 10 raised to 5 Pascal or 10 raised to 5 Newton per meter square. Okay. So this 0.25 bar means 0.25 into 10 raised to 5 Newton per meter square. Similar way, the partial pressure of carbon dioxide and the other end is also can be converted into this form. Okay, it's not 0.31, this is actually 0.031. Okay, that's a mistake. This is the final answer. 0.0312 into 10 raised to 5 Newton per meter square. Then this is the main equation we'll be using, the molar flux equation in equimolar diffusion. Okay, it's actually number of moles. So flux means when it divided by area, it becomes flux. If the area is not there, simply it is molar flow rate. So flux means molar flux means number of moles by area in equal to dAB into concentration difference Ca1 minus Ca2 by L. Okay, but we only have the values of partial pressure at both end. We don't have concentration. Okay, and this diffusion coefficient, I have taken the actual value of this from data book. Or you can take also do by taking the value from the given data. But sometimes diffusion coefficient may not be in the question, and that has to be taken from the data book. And according to the data book, this is actual diffusion coefficient. You can choose any value and do the take a diffusion coefficient. Okay, so what I'm saying is that we only have the in the main equation we have concentration difference, the difference Ca1 and Ca2, but we have only partial difference, partial pressure Pa1 and Pa2. So there's a relation between concentration and partial pressure. Ca will be Pa by RUT. RU means universal gas constant. So we can rearrange the equation and write like this. Okay, I will be NCO2 by A, that molar flux of first gas, carbon dioxide, equal to the Ca will be replaced by Ba by RUT. Okay, so this will be the new equation. Now we have partial pressure. We know about the value. So simple substitution, you get if we find NCO2 by A, if I am not multiplying with the area term, figure the area is you know where I haven't written the area, but you can find the area. This area is 5d square by this area is by d square power. If it is NCO by A means it means it is molar flux. So we have to find the molar rate for flow rate in order to find the mass flow rate. So I cannot put the A. So this A will be in this side. Okay, there will be A will be multiplied along this side. I forgot to write that. And this area can be find out by using this formula 5d square 4. And we have D in the question it is given D. Okay, so final answer will be 1.05 into 10 raised to minus 7 kilogram mole per second. So this is the molar flow rate. So how do you find mass flow rate or mass transfer rate? Just have to multiply the molar flow rate with the molecular weight. Okay, because the ratio of mass flow rate and molar flow rate will be molecular weight. So if we have the molar flow rate, then multiply it by molecular weight, we get the mass transfer rate of flow rate of carbon dioxide. That will be around 4.6 into 10 raised to minus 6 kilogram per second. So we got the first part that the mass transfer rate of carbon dioxide has 4.60 into 10 raised to minus 6 kilogram per second. So this is one important point you have to remember that for equimolar diffusion, counter diffusion, and we will be having two compounds in right. Here in the case we have carbon dioxide and air. The molar, the molar flow rate will be same for both the constituent, but it will be same in magnitude in opposite sign. Okay, here so I can write NCOT equal to minus N of air. Okay, that means the molar flow rate or molar flux anyway it will be same. That will be molar like flux or flow rate will be same as the other constituent. Only difference is there will be negative sign. Okay, so here I can write it as either molar flux same or molar flow in either way will be same because that area in the denominator will be cut, right? So either way it is correct. You can just learn it by the molar flux is same. So to find so that means the molar uh, flux or molar flow rate of air is same as carbon dioxide. So that means the molar transfer rate of air means it's the molar transfer rate of carbon dioxide which is found earlier, same value. So only difference will be the molar weight. Okay, assuming the air to be oxygen, I will be 28. So so we got the mass transfer rate as 3.04 into 10 raised to minus 6 kilogram per. So you can write, you can use either N or M, either way it is correct. So now we got the mass transfer rate of air also. So this is the way to do the problem.